Hello, welcome to today's video. Today we're looking at how to do volumes of revolution, but now with parametric equations. So I'm going to assume you already know what volumes of revolution is. I'm also going to assume you already know what parametric equations are, and therefore all we're doing is we're just mashing those two ideas together basically, and therefore launching straight into it. If you want to do volumes of revolution formed by rotating a region about the x-axis, it's just the following formula. It'll be pi lots of the integral of y squared, but this time y squared or the equation for y is not just going to be an equation of y related to x, it's going to be an equation relating y to the parametric variable t or theta. And then we're going to be multiplying that by dx over dt, which of course is the exact same adjustment we usually make when doing integration for parametrics anyway. And then we're going to be integrating the t's. However, something also to be aware of is the fact that because we're doing parametric integration, the limits are t values or theta values. So of course, as we're rotating about the x-axis, the limits would normally be x values, and it's just the equivalent t values for those x values that you use as the limits for our parametric integral. But then if you want to do volumes of revolution rotated about the y-axis, that would instead be the formula pi lots of the integral of x squared. Again, this time x being instead of in terms of y will be in terms of t or theta. And then we will multiply that by dy over dt. And then we're going to be integrating t's. So there you go. Those are the two formulas you need to know in order to be able to do this. Not in the formula booklet, but as I've kind of already pointed out, they're just mashing together two ideas you've already separately meant to know off by heart anyway, so it's not the worst thing in the world to remember, in my personal opinion. So we're going to be doing two examples of this in this video, and I've purposely chosen two not so nice examples to do, so I apologize for that in advance, but I've done that on purpose because I'm using this video basically as an excuse to do some revision of the hardest level of Maths A level integration while we're at it. So apologies if these integrals do look a bit more horrible, but it is just using these formulas in terms of the understanding how volumes of revolution for parametrics part of this stuff goes. So the first example is this. We have got some parametric equations. We're rotating about the y-axis. That's important to always note so you know which formula you're using. And luckily they have already given us the limits in terms of t. So we're not going to do any conversions this time. But that is something to sometimes watch out for. And also do be aware that we need to give our answer to one decimal place in the final answer. So therefore, let's get going. So just straight away, we can start using the formula. But before we do that, we remember that we're going to, as we're rotating about the y-axis, we're going to need to involve dy over dt. So I'm going to start by differentiating our y equation with respect to t, so that's already prepared. 1/7 e to the 7t, well, you just multiply by the number that's in front of the algebra, rather, I should say, just in front of the t to the power 1 in the power, so therefore it's 1/7 times by 7, which is 1, so therefore it's just e to the 7t is what 1/7 e to the 7t differentiates to, and then 1/8 t just differentiates with respect to t to just 1/8. Nice and easy. So therefore our integral will be pi lots of the integral from 0 to 0.3 as our t values, t limits. We're going to have x all squared, so that would be 4 lots of the square root of t all squared times by our dy over dt, which was e to the 7t plus 1/8. And then we're going to be integrating all of that with respect to t. So that's what we've got to do to complete this question. Okay, so continuing this on, we would then want to do the x squared bit, so square out the 4 square root of t squared part, and that would end up getting us, of course, just 16t, which is quite nice. And then we've got to be multiplying that by e to the 7t plus 1/8. And then we can simplify that because we'll need to do that before we're able to integrate. So therefore we'll have the integral of 16t e to the 7t and then 1/8 times 16t will just be 2t, which is quite nice to deal with. Cool. Now we've got to do that integration. Now, because there's that plus symbol there, we can effectively treat the integral like two mini integrals. The 2t can be integrated separately, and that'll be easy to do. It's just a classic add 1 to the power, divide by the new power trick. But then for the 16t e to the 7t part, we're going to need to use integration by parts. We know it's integration by parts because we've got that something times by something else sort of structure going on there. And we do have a very suitable thing to choose as our u, the thing we differentiate as part of the formula, because we've got a polynomial. So that's a good choice to do. So we can go and do that. I'll do the working for that over here. So I'm going to say let my u be 16t. My dv over dt would be e to the 7t. And that's, by the way, something to point out as part of this. It's a really good idea to show the workings for this. The advanced level students will sometimes just go, oh, I'll try and do integration by parts in my head. And it, unsurprisingly, sometimes goes wrong. Not because they don't know how to do integration by parts, but just because they're trying to do too much in one big go, and they make it the silliest of silly mistakes. So, yes, differentiate the u. The v, dv over dt, needs to be integrated to get v. So therefore, that'll be 1/7 e to the 7t. And therefore, integration by parts says that we'd end up with the u times the v, which would be 16 over 7t e to the 7t. And that's going to be evaluated between 0 and 0.3. We're then going to be taking away the integral of du over dt times by v, which would be just 16 over 7 e to the 7t. dt integrate between 0 and 0.3. And then also we got to integrate the plus 2t, and the plus 2t would integrate to t squared. And therefore we're doing t squared between 0.3 and 0. Just make it clear, 2t integrates to 2t squared over 2, and just the 2 over 2 cancels out. And you might notice I've put these giant brackets in to make sure all of this stuff is being multiplied by pi, because that's the really easy stuff to end up forgetting to do. So now we've got to do the final integral we haven't yet done. So therefore we're going to have the 16 over 7t e to the 7t. We've then got the integral of the 16 over 7 e to the 7t, which just means we're going to divide by 7 again, which would be 16 over 49 e to the 7t. And then we've got the plus t squared. And all of that's being evaluated between 0.3 and 0. Now, all you got to do is plug 0.3 into all of that stuff first, and then plug in 0, and you will get your answer. So sort of cramming it in this corner, 0.3 e to the, well, it'd be 2.1 minus 16 over 49 e to the 2.1 plus 0.3 all squared minus, cramming in, as I said, plugging 0 into all those things. Now, the thing to point out is, of course, 16 over 7 t times e to the power of 7t will become 0 when you plug 0 in because of the t. But don't make the mistake of just assuming plugging 0 into things just automatically makes that thing always become 0. That's a big mistake where students make, and none so more to watch out for that than in this integral, because minus 16 over 49 e to the 7t won't become 0 when you plug 0 into it. It will become minus 16 over 49. And then plus the t squared will become 0. Cool. And then you just got to do a bunch of number crunching on the calculator. And as the question wanted the answer to 1 decimal place, we're not going to leave it in exact form. Thank goodness, because this would be horrible in exact form. But if you do that, you'll get 10.523 ... So to 1 decimal place, that's 10.5. So there you go. That is the answer to this example. Nice. So some good skills in there. Let's do another example. So on this particular question, we have got a lot going on. We've got, of course, again, the parametric equations, but this time we are rotating about the x-axis. That's something to watch out for. The other thing to watch out for is, as we're rotating about the x-axis, we're expecting x values to be the things that define where we start and end our integral, but because we're doing it parametrically, we don't want x values, which is a shame because that is what they've given us. They've given us x values. So the first thing we need to do is we actually need to convert the limits. So let's start off by doing that. We therefore know that x is equal to this equation up above here. So therefore we just set that equal. Now conveniently, because both our limits have luns in, we can just jump straight to saying the luns don't really contribute much here. And so therefore we have tan of a half theta equals, for instance, minus 1 plus root 2. Now interestingly, this particular question doesn't have an interval for theta, which might be a problem at first glance, but actually in reality won't be, just because all the things we're dealing with here are periodic, so it wouldn't really matter. But to make your life easier, we're going to do between 0 and 2 pi. But anyway, the limit associated with minus 1 plus root 2 will end up being, if you solve that equation, you'll get a half theta equals pi over 8. And if you then solve that, you'll get theta equals pi over 4. So that's one of our limits. And then the other limit is going to be obtained from doing root 3 over 3 equals tan of a half theta. And from that, you'll get a half theta equals pi over 6, which of course will lead us to theta equals pi over 3. So those are our two limits. We are then also going to have to plug the parametric equations into the volumes of revolution parametric integral formula. So to do that, we need dx over dt. So that means we're also going to have to differentiate this thing. Now, you could just go and try and differentiate ln of tan of a half theta yourself. You, of course, have to use chain rule in order to do that, but there is an easier way, because if you take a look at the Maths A-level formula booklet, you'll probably first scroll to the differentiation section, and you'll find ln of tan of a half theta is not there. Ooh. However, if you then look in the integration section, you'll notice that ln of tan of a half theta appears in the right-hand column for the integral of cosec x. And that's important because it means if cosec integrates to ln of tan of a half theta, that tells you that ln of tan of a half theta differentiates to cosec theta. So that saves a lot of time straight away. So therefore we have that dx over d theta is just equal to cosec theta. We could then start getting the formula for the integral to do the volumes of revolution, which would then be pi lots of the integral, using our limits that we just found before, which was from pi over 4 to pi over 3. We'll have our y squared, which if you looked before, looking back, was the square root of cosec theta all over 2 cot cubed theta, and we're just going to be squaring that. So that doesn't look particularly nice, but don't worry, we will be able to do it. And then we've got our dx d theta as well, and then we're integrating with respect to theta. So of course the first thing you want to do is simplify the integral, and if you were to do that, you will quickly realize that the squared and the square root on the top are going to cancel out, so you just end up with a cosec theta on the top. That's then being multiplied by another cosec theta, so actually in total we're going to have a cosec squared theta on the top of the integral. And then on the bottom we're going to be squaring the 2 to get 4, and then we're going to be squaring cot cubed theta to get cot to the power of 6 theta. So there you go. That is what we have to integrate. Now, we are going to now approach doing the integral of that. There are lots of different ways of doing this, but I am going to approach this in the particular way that I'm going to approach it, just as an excuse to get people familiar with being able to integrate things involving cosec and cot. There is a way you could convert everything to sines and cos things and do a bunch of simplification and go from there, but that's going to take ironically longer, arguably, than what I'm going to do. So all I'm going to do is I'm going to do either some people are able to just do this by inspection, or you could, if in doubt, do the classic integration by substitution. Because the thing is, you look at this fraction, you go, oh, that looks horrible. And the bit that looks most horrible is you realize that the bottom looks particularly horrible. So therefore we could let u equal cot theta. We can then go ahead and differentiate that, which would find us du over d theta. And don't waste time, just realize that this is in the form booklet. So you can instantly look in the form booklet and see that cot theta differentiates to minus cosec squared theta. And that's personally why I'm choosing to leave everything still in terms of cot and cosec, because actually it's not too bad, because half the things you need to know are in the form booklet for this stuff. Some people are then very comfortable with what to do with this derivative to then be able to do integration by substitution. I, and along with other people, sometimes prefer to rearrange this differentiated substitution to make it d theta equals, to be able to replace that in the original integral. If you do that, you will end up with an expression for that being, making d theta the subject of the formula, minus 1 over cosec squared theta du, and therefore our integral will become pi lots of the integral from, well, we'll deal with those limits in a bit, but we have the minus sign being introduced because of the d theta substitution. The cosec squared theta we had on the top being cancelled out by the 1 over cosec squared theta being introduced by the du. On the bottom, we still have the 4, but then the cot to the power of 6 theta is then just becoming u to the power of 6. And therefore integrating that with respect to u. And so then converting the limits as well, we'd then realize that if we wanted to convert pi over 3, we'd just plug it into our substitution. So cot of pi over 3, which, funny enough, is, let's have a think. That would be root 3 over 3. And then also we could do the same with the other limit. So cot of pi over 4, which is conveniently just 1. So that's quite nice. And then, therefore, we can just go ahead and integrate, because this is the same as, of course, again, a silly mistake that people make. Realize this is minus 1/4 u to the power minus 6 du, because people make the mistake of sometimes moving the 4 up to the top. Another thing to watch out for, by the way, I didn't mention with the limits, is it's your natural instinct is to go, oh, 1's the bigger number. 1 is bigger than root 3 over 3, so put 1 as the limit at the top, and the root 3 over 3 is the limit on the bottom. But, controversially, no, because you've got to place the limits where they are replacing their original limits. So as root 3 over 3 was associated with pi over 3, and pi over 3 was the limit at the top, the replacement root 3 over 3 has to go at the top. You are welcome to do some adjustment with the limits to do with the minus sign as well, if you want, but you know, technically this is the way the limits have got to go in the integral in the format I've currently got it in. So therefore we can now just go ahead and do that integral, because it's actually very easy now, because we add 1 to the power, which would be power of minus 5, and then we divide by minus 5, which will get positive 1 over 20, because the minus 1/4 divided by minus 5. And then you just got to plug those limits in, and we will have our answer. Now, if we go ahead and do that, it doesn't look particularly nice at first. We've got 1 over 20, lots of 1 over root 3 over 3 to the power of 5. Take away 1 over 20, lots of 1 over 1 to the power of 5. And so that doesn't look particularly nice, but you can then just evaluate it. Root 3 over 3 to the power of 5 would be 9 root 3 over 243, but then we're doing 1 over it. So basically, it's just going to end up becoming just 9 root 3. So therefore, we've got 1 over 20 lots of 9 root 3. And then we've got the 1 over 1 to the power of 5, which of course is just 1. And we've got 1 over 20 lots of that as well. So I guess I could factorize it. So basically, point is, the final answer is pi over 20 lots of 9 root 3 minus 1. And there you go. That is the final answer, and that is the end of our second example. Hopefully you found today's video useful. I got to show you some pretty crazy integration, but I will see you, I'm sure, in a future video. Goodbye.